Now, in this lecture, we'll find out the area of the green shape. In the drawing, we have a circle. We know that the radius of this circle r equals to 2 units in its length. In addition, inside this circle, we have peripheral angle ACB that is equals to 70 degrees in its size. And we also have this is a common external point P. For the common external point P, this point, we have two tangents to this circle. Tangent PA, that is tangent to this circle at point A, and tangent PB, that is tangent to this circle here at point B. Our mission is to find out the area of this green shape. Point O is the center of the circle. So we join points O and B together by a straight line. So point O is the center of the circle, and point B is the point of the circle itself. Therefore, line segment OB is the radius of the circle, that is equal to 2 units according to what is given as the question. Here we will implement rule 1. I repeat quickly on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So, in the drawing we have a circle, and we also have tangent AB that is tangent to this circle here, at this point, point M. And we have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 1. We can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius OB is equal to R. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees, according to rule 1, of course. Likewise, according to the same rule, rule 1, we have the radius OA of this circle that is drawn to point A, that is the point of tendency of tangent PA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees. In the next step, I'll present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. Repeat again, on rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So, in the drawing, we have a circle. Inside this circle, we have peripheral angle ACB. This peripheral angle ACB equals to theta in its size, and it is subtended on arc AB. We also have in this drawing the central angle AOB that is subtended on the same arc, arc AB. And therefore, the central angle AOB that is subtended on the same arc as the peripheral angle ACB will be twice as large is the central angle AOB. And because of the fact that the peripheral angle ACB equals to theta, it means that the central angle must be equal to 2 theta. The twice as large as this peripheral angle is equal to theta. We can implement all 13 in our drawing. Why? Because in our drawing we have peripheral angle ACB that is equal to 70 degrees in its size, and this peripheral angle ACB is subtended on RKB. And we also have the central angle AOB that is subtended on the same arc RKB. Therefore, according to Rule 13, the central angle AOB must be twice as large as this peripheral angle, the ACB, that is equal to 70 degrees in its size. Therefore, the size of the peripheral angle must be equal to 70 degrees times 2, that is 140 degrees. In conclusion, we found out that the size of this peripheral angle AOB is 140 degrees. In the next step, we will join points P and O together by a straight line. By joining points P and O, we created two right triangles. We have the upper right triangle AOP and the lower right triangle BOP. So in the next step, we'll prove that those two right triangles can go into each other. Repeat again, we'll prove that the upper right triangle AOP is congruent to the lower right triangle BOP. So, why those two right triangles can go into each other? First of all, side AO of the upper right triangle AOP is equal to side BO of the lower right triangle BOP. Repeat again, side AO of the upper right triangle AOP equals to side OB of the lower right triangle BOP. AO equals to OB. They are both the radii of this circle, therefore they are equal to each other. Repeat again. Side AO of the right upper triangle AOP equals to side OB of the lower right triangle BOP. They are both the radii of the circle, therefore they are equal to each other. Each side equals to 2. The radius of the circle is 2. In addition, we have side OP that is a common side, it belongs to both triangles. So we can write down that OP equals to itself. It's a common side that belongs to both triangles. And finally, side AP of the right upper triangle APO equals to side BP of the right lower triangle BPO. So AP equals to BP according to rule 2. I repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle and we also have this common external point, point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule 2 in our drawing. Why? Because in our drawing, we have the common external point P. From the common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. Repeat again. PA equals to PB. According to rule 2. So actually found out that all the three sides of this right upper triangle AOP are correspondingly equal to all the three sides of the right lower triangle BOP. Therefore, those two right triangles can go into each other according to side rule. So I write it down. The right upper triangle AOP is congruent. This is the sign of congruent to the right lower triangle BOP, according to side rule. And from the fact that those two right angles can go into each other, we derive that those two angles must be also equal to each other, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right angles can go into each other, therefore the two corresponding angles, those two corresponding angles must be also equal to each other. The conclusion found out that angle AOP in the right upper triangle APO is equal to angle BOP, this angle BOP, in the right lower triangle BPO. Okay, angle AOP equals to angle BOP. So if we define this angle as alpha, then the angle must be also equal to alpha because they are equal to each other. Okay. So actually alpha plus alpha, total alpha plus alpha equals to this big angle. And this big angle, we will find out that this big angle BOA equals to 140 degrees in its size. So in conclusion, we found out that alpha plus alpha equals to 140 degrees. Alpha plus alpha equals to 140 degrees. That is to say 2 alpha equals to 140 degrees. Here we divide this equation by 2 and finally we get that the missing angle alpha equals to 140 degrees over 2, it is 70 degrees. So, actually this is angle alpha that is equal to 70 degrees in its size. And this angle is also angle alpha, that is equal to 70 degrees in its size. In the next step, we'll focus on the right upper triangle, triangle APO. On the right upper triangle, triangle APO, tangents 70 degrees. What is the value of tangent 70 degrees? From the drawing, it is very easy to see that tangent 70 degrees equals to AP over AO. Again, tangent 70 degrees in the right triangle APO equals to AP over AO. AP is the missing side, so we leave it as it is. So it is AP over AO. Here AO is the radius of this circle is equal to 2, therefore we substitute AO by 2. So in conclusion, found out that tangent 70 degrees equals to AP over 2. Here we will multiply this equation. Here tangent 70 degrees is equals to AP over 2. So here we will multiply this equation by 2, and finally we will get that 2 times tangent 70 degrees equals to AP. Tangent 70 degrees is 2.75. So we found out that 2 times 2.75 equals to AP. 2 times 2.75 is 5.5. In conclusion, we found out that side AP this is side AP, and it equals to 5.5 units in its length. So, what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP so the area of the upper right triangle AOP plus the area of the lower right triangle BOP will give us in total the area of quadrilateral AOBP, and then we have to subtract the area of sector AOB from the area of quadrilateral AOBP. We have to subtract the area of sector AOB from the area of quadrilateral AOBP. Repeat again, we can find out that in total the area of the green shape is equals to the area of the right triangle AOP plus the area of the right triangle of the lower right triangle BOP. The sum of the areas of those two right triangles will give us the area of quadrilateral BOAP, and then we have to subtract from the area of quadrilateral AOBP the area of sector AOB. Here, the rounded line above AOB is the sign for a sector. It means sector AOB. And this code bracket is assigned for the area, so in total this expression means the area of sector AOB. Okay. Repeat again. The area of quadrangle AOBP, that's actually the sum of the areas of the right upper triangle AOP plus the right lower triangle BOP. So the area of quadrangle AOBP minus the area of this sector AOB will give us the area of this green shape. Okay. So in the next step, I present to you the concept of sector. What is the sector? A sector is part of a circle. The green shape AOP is a sector. This sector AOB consists of two radii of this circle and the arc between those two radii. AO is the first radius, BO is the second radius of the circle, and here AB is the arc between those two radii. And the angle between the two radii of this circle is angle theta. We can also define that the sector consists of two legs. The first leg is AO and the second leg is BO. Both those two legs are the radii of this circle, and the sector also consists RKB, that is between the two legs that are the radii of this circle. And angle theta is the angle between the legs AO and BO of this sector. So, what is the area of this sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is actually pi r squared, because the radius is r, times the angle between the legs of this sector, that is theta, over 360 degrees. Repeat again, the area of this sector AOB equals to pi r squared times theta over 360 degrees. Okay. We have already found out that the areas of those two right angles, actually we have already found out that those two right angles can go into each other, therefore they have also the same areas. Okay. That is to say, the area of the right upper triangle AOP equals to the area of the right lower triangle BOP. Therefore, we can substitute the area of the right lower triangle BOP by the area of the right upper triangle AOP. So we'll do it now, and we'll get that the area of the green shape in total equals to the area of the upper right triangle AOP plus the area of the right lower triangle BOP. We substitute the area of the right lower triangle BOP by the area of the upper right triangle AOP because they are equal to each other. Minus the area of sector AOB. So the area of the right upper triangle AOP plus the area of the right triangle AOP is 2 times the area of the upper right triangle AOP. Minus the area of sector AOB. So first of all, we have to find out the area of the right upper triangle AOP. What is the area of the right upper triangle AOP? we know that the area of any right triangle equals to the base of the triangle times the height to the base over 2. We choose the base of this right triangle AOP is AO, and therefore the height to the base will be AP. Why? Because AP creates 90 degrees with the height. The height AP creates 90 degrees with the base AO. So the base is AO, and the height to the base is AP divided by 2. The base AO is equal to 2 units because it is the radius of the circle is equal to 2. So AO equals to 2. We have already found out that AP equals to 5.5 units. So it is 2 times 5.5 divided by 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. And we left only with 5.5. So in conclusion, we found out that the area of the upper right triangle AOP is equals to 5.5 square units. So 2 times the area of the right triangle AOP is 5.5 times 2, that is 11. So 11 is the sum of the areas of those 2 right triangles. That is actually also the area of quadrilateral AOBP, and we have to subtract from the area of quadrilateral AOP the area of this sector, sector AOB. So the area of the green shape in total equals to 11 was the area of sector AOB. So in the next step, we calculate and find out the area of sector AOB. So what is the area of this sector, sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is actually pi r square, times the angle between the legs of this sector AOB. This angle, the angle between the legs of sector AOB is this angle, it is actually 140 degrees over 360 degrees. Hit again. The area of sector AOB equals to the area of the circle that contains the sector that is pi r squared times the angle between the legs of the sector that is 140 degrees over 360 degrees. So the area of sector AOB equals to pi r squared. R is 2, therefore r squared is 2 squared, that is 4. So the area of the circle that contains the sector AOB is 4 pi times 140 degrees over 360 degrees. So this expression in total is equals to 4.888 square units. We can very found out that the area of sector AOB in total it is equals to 4.888 square units. Okay. So the area of the green shape is equals to the area of quadrilateral AOBP, that is the sum of the areas of the upper right triangle AOP plus the area of the lower right triangle OBP, and we already found out that the sum of the areas of those two right triangles is equals to 11 square units, minus the area of this sector, sector AOB, and we just right now found out that the area of sector AOB equals to 4.888 square units. And 11 minus 4.888, it is equals to 6.111 square units. And we found out that the area of the green shape equals to 6.111 square units. And this is the answer to the question. Repeat again. The area of this green shape is equals to 6.111 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. In the drawing, we have this circle. We know that the radius of this circle r equals to 2. Inside this circle, we have peripheral angle ECB that is equals to 70 degrees in its size. In addition, we have in this drawing the common extreme point, point P. From the common extreme point, point P, we have two tangents to this circle, tangent PA and tangent PB. And our mission is to find out the area of this green shape. The center of this circle is here at point O. So, first of all, we join points O and B together by a straight line. Point O is the center of the circle, point B is the point of the circle itself, so for OB is the radius of the circle that is equal to 2. Then we implemented in this drawing rule 1, and according to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So we have here the radius OB that is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees. Likewise, according to the same rule, rule 1, we have the radius OA that is drawn to point A, that is the point of tendency of tangent PA with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees according to the same rule, rule 1. In the next step, I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. Repeat again on rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. Okay? So in the domain we have a circle. Inside this circle we have the peripheral angle ACB that is equals to theta degrees in its size, and this peripheral angle ACB is subtended on this arc RKB. In addition, we also have this drawing the center angle AOB that is subtended on the same arc RKB. And therefore, according to this all 13, the center angle that is subtended on the same arc as the peripheral angle. So the size of the center angle must be twice as large as the size of this peripheral angle ACB. And because of the fact that the size of peripheral angle ACB is theta, therefore the size of the center angle AOB must be equal to 2 theta, because they're both subtended on the same arc. We actually can implement all 13 in our drawing. Why? Because in our drawing we have peripheral angle ACB. This is peripheral angle ACB that equals to 70 degrees in its size, and this peripheral angle ACB is subtended on this arc RKB. And we also have here the center angle AOB. This is the center angle AOB that is subtended on the same arc RKB. Therefore, according to Rule 13, because of the fact that those two peripheral angle and the center angle they subtended on the same arc, the size of the center angle AOB must be twice as large as the size of this peripheral angle ACB. The size of the peripheral angle ACB is 70 degrees, therefore the size of the center angle AOB must be equal to 70 degrees times 2, that is 140 degrees. Okay, so here we implemented Rule 13 in our drawing. And therefore, according to Rule 13, the size of the center angle AOB must be equal to 140 degrees. Okay, so in the next step, we join points O and P together by a straight line. By joining points O and P, we created here two right angles. We have the upper right angle AOP, and we have the lower right angle, triangle BOP. The next step, we actually proved that those two right angles can go into each other. So why those two right angles can go into each other? First of all, side AO of the right angle AOP is equal to side BO of the right lower triangle, triangle BOP. Why? Because they are both the area of the circle, therefore they are equal to each other. Repeat again. Side AO of the right upper triangle APO equals to side BO of the right upper triangle of the right lower triangle POB. They are both equal. They are both the area of the circle, therefore they are equal to each other. In addition, we have side PO is a common side that belongs to both triangles, so we can write down that PO equals to itself is a common side that belongs to both triangles. PO equals to PO is a common side, and finally, side PA equals to side PB. Side PA in the right upper triangle APO equals to side PB in the right lower triangle, triangle PBO, according to Rule 2. Repeat again quickly Rule 2. According to Rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the domain we have a circle and we have this common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, Rule 2, they are equal to each other. That is to say, PA equals to PB. We implemented Rule 2 in our drawing. In our drawing, we have the common external point P. From the common external point P, we have two tangents to this circle, tangent PA and tangent PB. According to Rule 2, they are equal to each other. That is to say, PA equals to PB. Repeat again. PA equals to PB according to Rule 2. So we actually found out that all the three sides of the upper right triangle POA are correspondingly equal to all the three sides of the right lower triangle PBO. Therefore, we actually proved that those two right triangles can go into each other according to side rule. Okay, and from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right angles congruent to each other, therefore the two corresponding angles, those two corresponding angles must be also equal to each other. So if I found out that angle AOP in the right triangle AOP equals to angle BOP in the right triangle BOP, according to the rule that I mentioned. So if we define the size of this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha, in total, they must be equal to this angle. That's actually 140 degrees. So alpha plus alpha equals to 140 degrees. That is to say 2 alpha equals to 140 degrees. We divided this equation by 2 and finally found out that the missing angle alpha equals to 140 degrees over 2, that is 70 degrees. So this is angle alpha that is equal to 70 degrees in its size, and this is also angle alpha that is equal to 70 degrees in its size. Then we focus on this right upper triangle APO, and the right upper triangle APO, triangle 70 degrees equals to AP over AO. Again, triangle 70 degrees equals to AP over AO. Triangle 70 degrees equals to AP over AO. AP is the missing side, so we leave it as it is. So it is AP over AO. AO is 2, it is the radius of the circle, that is 2. So in conclusion, we found out that triangle 70 degrees equals to AP over 2. We multiply this equation by 2 and finally found out that 2 times triangle 70 degrees equals to AP. So 2 times triangle 70 degrees. Triangle 70 degrees is 2.75. So 2 times 2.75 is equals to AP. 2 times 2.75 is 5.5. So in conclusion, found out that the length of side AP is 5.5 units. Our mission is to find out the area of this green shape. The area of the green shape from the drawings is very easy to see that the area of the green shape equals to the area of the upper right triangle APO plus the area of the lower right triangle BPO. So the sum of the areas of those two right angles will give us the area of quadrilateral APBO. So the area of quadrilateral APBO minus the area of this sector ABO will be equal exactly to the area of this green shape. Repeat again, the area of the green shape in total equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP. The sum of the areas of those two right triangles will give us the area of quadrilateral APBO. And when we subtract the area of sector AOB from the area of quadrilateral APBO, we will get exactly the area of this green shape. So we have already found out that triangle AOP can go into triangle BOP, therefore they also have the same areas. Therefore we can substitute the area of triangle BOP by the area of the right upper triangle AOP, because they have the same areas. So we did it, and we got that the area of triangle AOP, the area of the green shape equals to the area of triangle AOP, plus the area of triangle BOP, that equals to, we substitute the area of triangle BOP by the area of triangle AOP, because they are equal to each other, minus the area of sector AOB. The area of triangle AOP plus the area of triangle AOP, 2 times the area of triangle AOP, minus the area of sector AOB. So we have to find out the area of triangle AOP. What is the area of triangle AOP? The area of any triangle equals to the base of the triangle times the height to the base over 2. So what is the area of this right triangle AOP? We choose the base as AO and the height is AP. The base is AO and the height is AP. Repeat again. The base of the right upper triangle AOP is AO and the height to the base is AP divided by 2. AO is the radius of the circle, that is 2. AP equals to 5.5 divided by 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled and we left only 5.5. So in conclusion, we found out that the area of the upper right triangle AOP equals to 5.5 square units. Repeat again, the area of this upper right triangle AOP equals to 5.5 square units. Okay? And we have actually found out that the area of the green shape in total it is equals to 2 times the area of the right upper triangle AOP minus the area of sector AOB. So the area of the right upper triangle AOP is 5.5 square units. So 2 times 5.5 is 11. So in total the area of the green shape equals to 11 minus the area of sector AOB. Now we have to find out the area of sector AOB, and in this way we find out the area of the green shape. So what is the area of this sector AOB? The area of sector AOB will be equal to the area of the circle that contains the sector AOB. The area of the circle that contains sector AOB is pi r squared. Yeah. The area of sector AOB equals to the area of the circle that contains the sector that is pi r squared times the angle between the legs of this sector AOB that is 140 degrees over 360 degrees. Again, times the angle between the legs of sector AOB that is 140 degrees over 360 degrees. The radius of the circle r is 2, therefore r squared is 2 squared. So in total, the area of the circle that contains sector AOB is pi r squared, that is 4 pi, because r squared is 4. And in total, this expression 4 pi times 140 degrees over 360 degrees, it is equals to 4.888 square units. In conclusion, we found out that the area of this sector AOB equals to 4.888 square units. Okay, so the area of this green shape equals to the area of quadrilateral AOBP. And we already found out that the area of quadrilateral AOBP is 11 square units minus the area of this sector AOB. And we just right now found out that the area of sector AOB is 4.888. So 11 minus 4.888 is the area of this green shape. 11 minus 4.888 is 6.111. In conclusion, we found out that the area of this green shape is equals to 6.111 square units. Okay, thank you very much.